Hello and welcome. In this video, we will explore several advanced applications of definite integrals, which are key topics in the IB Mathematics Analysis and Approaches higher-level curriculum. By the end of this session, you will be able to calculate the area between curves, find the volume of solids of revolution using both the disk and washer methods, and apply integration to solve real-world problems involving rates of change. We'll begin by revisiting the concept of area, but this time, we'll focus on finding the area of regions bounded by functions of y. Our first objective is to calculate the area of a region bounded by a curve and the y-axis. You are likely familiar with finding the area under a curve y equals f of x, bounded by the x-axis and vertical lines x equals a and x equals b. This is given by the integral from a to b of f of x dx. Now let's consider a region bounded by a curve x equals g of y, the y-axis and horizontal lines y equals c and y equals d. To find this area, we can use a similar approach, but we integrate with respect to y. We imagine slicing the region into thin horizontal rectangles. Each rectangle has a width of x, which is g of y, and a height of di. The area of one such rectangle is x di, or g of y di. To find the total area, we sum the areas of all these rectangles by integrating from the lower y bound c to the upper y bound d. This gives us the formula. Area equals the integral from c to d of g of y di. In other words, we integrate the function of y with respect to y. Let's work through an example to see this in action. Find the area of the region bounded by the curve x equals y squared plus 1, the y-axis, and the lines y equals 1 and y equals 2. First, let's visualize this. The curve x equals y squared plus 1 is a parabola opening to the right, with its vertex at 1, 0. The y-axis is the line x equals 0. The horizontal lines y equals 1 and y equals 2 define our vertical boundaries. The shaded region is the area we need to find. Notice that the curve x equals y squared plus 1 is always to the right of the y-axis in this interval, so our function g of y is positive. Now we apply our formula. The function is g of y equals y squared plus 1, and our bounds are c equals 1 and d equals 2. So the area is the integral from 1 to 2 of y squared plus 1d. Let's evaluate this integral. The antiderivative of y squared plus 1 is y cubed over 3 plus y. We evaluate this from 1 to 2. Plugging in the upper bound, we get 2 cubed over 3 plus 2. Plugging in the lower bound, we get 1 cubed over 3 plus 1. This simplifies to 8/3 plus 2 minus 1/3 plus 1. Combining the terms, we get 7/3 plus 1, which equals 10/3. Therefore, the area of the region is 10/3 square units. We have successfully used integration with respect to y to find the area. Now let's move on to our second objective, finding the volume of a solid of revolution. Imagine we have a 2D region, say the area under a curve y equals f of x from x equals a to x equals b. If we take this region and revolve it 360 degrees or 2 pi radians around the x-axis, we create a 3D shape called a solid of revolution. Our goal is to find the volume of this solid. To do this, we use a method called the disk method. We slice the solid into many thin disks perpendicular to the axis of revolution. Consider one such disk. Its radius, r, is the distance from the x-axis to the curve, which is simply the function value f of x. Its thickness, or height, is a small change in x, which we call dx. The volume of a single disk is the area of its circular face times its thickness. The area of a circle is pi r squared. So, the volume of one disk is p times the radius squared, times the thickness. Substituting f of x for the radius, we get pi times f of x squared, times dex. To find the total volume of the solid, we sum the volumes of all these infinitely thin disks by integrating from our lower bound a to our upper bound b. This gives us the disk method formula for revolution about the x-axis. Volume equals pi times the integral from a to b of f of x squared d, dx. This is also often written as pi times the integral of I squared dex. Let's apply this to an example. Find the volume of the solid formed when the region under the curve y equals x squared from x equals 0 to x equals 5 is revolved about the x-axis. Here, our function is f of x equals x squared, and our bounds are a equals 0 and b equals 5. Plugging these into the formula, we get volume equals pi times the integral from 0 to 5 of x squared dx. This simplifies to pi times the integral from 0 to 5 of x to the fourth dx. Now we find the antiderivative of x to the fourth, which is x to the fifth over 5. We evaluate this from 0 to 5. Plugging in the bounds, we get pi times 5 to the fifth over 5 minus 0 to the fifth over 5. 5 to the fifth over 5 is 5 to the fourth, which is 625. So the volume is 625 pi cubic units. We have now successfully used the disk method to find the volume of a solid of revolution about the x-axis. Our next objective is to find the volume of a solid of revolution about the y-axis. The process is very similar to revolving about the x-axis, but with a crucial difference. We now revolve a region bounded by a curve x equals g of y, the y-axis, and horizontal lines y equals c and y equals d around the y-axis. This creates a different type of solid. Again, we use the disk method, but this time we slice the solid into thin horizontal disks, perpendicular to the y-axis. For each disk, the radius r is the distance from the y-axis to the curve, which is x or g of y. The thickness is a small change in y die. The volume of one disk is p times the radius squared times the thickness. Substituting g of y for the radius, we get pi times g of y squared times die. Integrating from the lower y-bound c to the upper y-bound d gives us the total volume. The disk method formula for revolution about the y-axis is volume equals pi times the integral from c to d of g of y squared di. This is also written as pi times the integral of x squared di. A critical point here is that the function must be invertible over the interval of revolution. This ensures that for each y value, there is only one corresponding x value, so our radius is well defined. Let's work through an example. Find the volume of the solid formed when the region bounded by y equals the natural log of x, the y-axis, and the lines y equals 0 and y equals 1 is revolved about the y-axis. Our bounds are y equals 0 and y equals 1. However, our function is y equals ln of x. We need to express x as a function of y. To do this, we exponentiate both sides of the equation y equals ln of x. This gives us e to the power of y equals x, so our function g of y is e to the y. Now we can set up the integral. Volume equals pi times the integral from 0 to 1 of e to the y squared d. Using exponent rules, e to the y squared is e to the 2y, so we need to integrate e to the 2y. The antiderivative of e to the 2e is 1/2 e to the 2e. Evaluating from 0 to 1, we get pi times 1/2 e squared minus 1/2 e to the 0. Since e to the 0 is 1, the volume is pi over 2 times the quantity e squared minus 1 cubic units. We have now successfully found the volume of a solid of revolution about the y-axis by first inverting the function. Our next objective is to find the volume of a solid of revolution formed by revolving the region between two functions. What if the region we're revolving is not bounded by an axis, but by two curves? For example, suppose we have an upper function y equals f of x and a lower function y equals g of x, and we revolve the region between them about the x-axis. This will create a solid with a hole in the middle, like a washer or a donut. We call this the washer method. The idea is to find the volume of the outer solid, formed by revolving the upper function, and subtract the volume of the inner solid, formed by revolving the lower function. Imagine a thin washer-shaped slice. The outer radius, r, is the upper function f of x. The inner radius, er, is the lower function g of x. The thickness is dx. The area of this washer is the area of the outer circle minus the area of the inner circle. So the area is pi times the outer radius squared minus pi times the inner radius squared. This simplifies to pi times the quantity f of x squared minus g of x squared. The volume of the washer is this area times the thickness d. To find the total volume, we integrate this expression from the lower x-bound a to the upper x-bound b. This is the washer method formula for revolution about the x-axis. Let's see an example. Find the volume of the solid generated by revolving the region between y equals x squared and y equals the square root of x about the x-axis. First, we need to find the points of intersection to determine our bounds of integration. We set the two functions equal to each other. X squared equals the square root of x. Squaring both sides gives x to the fourth equals x. Rearranging, we get x to the fourth minus x equals 0. Factoring out x, we have x times the quantity x cubed minus 1 equals 0. This gives us solutions x equals 0 and x equals 1. These are our bounds. Next, we need to determine which function is the upper function f of x and which is the lower function g of x on the interval from 0 to 1. We can test a point, say x equals 0.5. At x equals 0.5, the square root of x is about 0.707, and x squared is 0.25. Since 0.707 is greater than 0.25, the square root of x is the upper function, and x squared is the lower function. Now we can set up the integral using the Washer method formula. Volume equals p times the integral from 0 to 1 of the square root of x squared minus x squared squared dx. This simplifies to pi times the integral from 0 to 1 of x minus x to the fourth dx. The antiderivative is x squared over 2 minus x to the fifth over 5. Evaluating from 0 to 1, we get pi times 1/2 minus 1/5 minus 0 minus 0. 1/2 minus 1/5 is 3/10. So the volume is 3 pi over 10 cubic units. We have now successfully used the Washer method to find the volume of a solid of revolution between two functions. Our final objective is to apply integration to solve problems involving rates of change. In differential calculus, we learned that the derivative of a function gives us its rate of change. For example, if a function v of t represents the volume of water in a tank at time t, then its derivative, v prime of t, represents the rate at which the volume is changing. Since integration is the reverse process of differentiation, we can use it to find the total change in a quantity over an interval, given its rate of change. The fundamental theorem of calculus states that the integral of a rate function, f prime of x, from a to b, gives the total change in the original function, f of x, over that interval. In other words, the area under a rate function's graph tells us the total accumulation of the quantity over that time period. Let's look at an example involving traffic flow. The rate of traffic flow past a pedestrian crossing between 8 a.m. and 8:30 a.m. is given by the function r of t equals t cubed over 80 minus t squared over 2 plus 4t plus 40, where t is the number of minutes after 8 a.m. The question asks, how many cars pass the crossing between 8 a.m. and 8:30 a.m.? This is a question about the total number of cars, which is the total accumulation of traffic. Since r of t is the rate of flow, we need to integrate it over the given time interval. The interval is from 8 a.m. to 8:30 a.m. Since t is minutes after 8 a.m., this corresponds to t equals 0 to t equals 30. So the total number of cars is the integral from 0 to 30 of r of t d. Let's find the antiderivative of r of t. The antiderivative is t to the fourth over 320 minus t cubed over 6 plus 2t squared plus 40. Now we evaluate this from 0 to 30. We plug in 30 for t, and then subtract the result of plugging in 0 for t. The terms with t all become 0 when we plug in 0. Calculating these values, we get 2531.25 minus 4500 plus 1800 plus 1200. This sums to 1031.25. Since we can't have a quarter of a car, we should round this to the nearest whole number. Therefore, approximately 1031 cars pass the crossing between 8 a.m. and 8:30 a.m. This demonstrates how integrating a rate function gives us the total change in the quantity. We have now covered several key applications of definite integrals. Let's quickly recap. We learned how to find the area of a region bounded by a curve and the y-axis by integrating with respect to y. We also explored the disk method for finding the volume of solids of revolution about both the x and y-axes. Finally, we introduced the Washer method for finding the volume of hollow solids, and we saw how integrating a rate function gives us the total change in a quantity. These techniques are fundamental for solving a wide range of problems in mathematics and science. To solidify your understanding, I've prepared some practice questions that reflect the style and difficulty you might encounter in the IBAAHL exam. Let's go through them one by one. Here is the first practice question. Take a moment to think about how you would approach this problem. Let's work through the solution. The region is bounded by the y-axis, so we should integrate with respect to y. This means we need to express x as a function of y. Starting with y equals e to the x, we take the natural logarithm of both sides to get x equals ln of y. This is our function g of y. The bounds of integration are given as y equals 2 and y equals 3. So the area is the integral from 2 to 3 of ln of yd. To solve this, we need to use integration by parts. Let u equal ln of y and dv equal d. Then do is 1 over yd and v is e. Applying the formula, we get y ln of y minus the integral of y times 1 over y di. The integral simplifies to the integral of 1 d, which is just y. So our expression becomes y ln of y minus y, evaluated from 2 to 3. Plugging in the bounds, we get 3 ln of 3 minus 3 minus 2 ln of 2 minus 2. Rearranging the terms, the exact area is 3 ln of 3 minus 2 ln of 2 minus 1 square units. Here is the second practice question. Pause the video and try to solve this one yourself. Let's go through the solution. We are revolving a region bounded by a single curve and the x-axis about the x-axis. This is a classic disk method problem. The formula for the disk method about the x-axis is v equals pi times the integral from a to b of y squared d. Our function is y equals x cubed, and our bounds are x equals 1 and x equals 2. Substituting these into the formula, we get v equals pt times the integral from 1 to 2 of x cubed squared dx. This simplifies to pi times the integral from 1 to 2 of x to the 6th dx. The antiderivative of x to the 6th is x to the 7th over 7. We evaluate this from 1 to 2. Plugging in the bounds, we get pi times 2 to the 7th over 7 minus 1 to the 7th over 7. 2 to the 7th is 128, and 1 to the 7th is 1. So the volume is pi times 127 over 7, or 127 pi over 7 cubic units. Here is the third practice question. This problem involves revolution about the y-axis. Give it a try. Let's solve it. We are revolving a region about the y-axis, so we need to integrate with respect to y. The formula is v equals pi times the integral from c to d of x squared di. First, we need to express x squared in terms of y. From y equals x squared, we already have x squared equals y. So our function is x squared equals y. Next, we need the bounds of integration. The region is bounded by y equals x squared, y equals 4, and the y-axis. The y-axis is the line x equals 0, which corresponds to y equals 0 on the parabola. So our bounds are from y equals 0 to y equals 4. Plugging these into the formula, we get v equals pi times the integral from 0 to 4 of y di. The antiderivative of y is y squared over 2. Evaluating from 0 to 4, we get pi times 4 squared over 2 minus 0 squared over 2. This simplifies to pi times 16 over 2, which is 8 pi. So the volume is 8 pi cubic units. Here is the fourth practice question. This problem involves two functions and revolution about the x-axis. Think about which method you should use. Let's solve it. Since we are revolving the region between two curves about the x-axis, we will use the washer method. The formula is v equals p times the integral from a to b of the upper function squared minus the lower function squared dx. First, we need to find the points of intersection to determine our bounds. We set the two functions equal to each other. X squared minus 4x plus 6 equals 6 minus x. Rearranging, we get x squared minus 3x equals 0. Factoring, we have x times the quantity x minus 3 equals 0. So our bounds are x equals 0 and x equals 3. Next, we need to identify the upper and lower functions. Let's test a point between 0 and 3, say x equals 1. At x equals 1, the parabola is at y equals 3, and the line is at y equals 5. Since 5 is greater than 3, the line is the upper function, and the parabola is the lower function. Now we set up the integral. V equals pi times the integral from 0 to 3 of 6 minus x squared minus 4x plus 6 squared. Expanding the terms inside the integral gives us a polynomial. Integrating this polynomial term by term and evaluating from 0 to 3 is a straightforward but lengthy calculation. After expanding and integrating, we find the volume is 108 pi over 5 cubic units. This problem highlights the importance of careful algebraic manipulation in the washer method. Here is the fifth and final practice question. This is a rates of change problem. How would you find the net change in water volume? Let's solve it. The net rate of change of water in the kayak is the rate of water leaking in minus the rate of water being bailed out. Let's call this net rate R of t. So R of t equals R1 of t minus R2 of t. Substituting the given functions, we get R of t equals 5 minus 5e to the negative 0.2t minus the quantity 6 minus 6e to the negative 0.1t. Simplifying this expression, the net rate is 6e to the negative 0.1t minus 5e to the negative 0.2t minus 1. To find the total amount of water after 10 minutes, we integrate this net rate from t equals 0 to t equals 10. The total volume is the integral from 0 to 10 of R of t dt. Let's find the antiderivative of each term. The antiderivative is negative 60e to the negative 0.1t plus 25e to the negative 0.2t minus t. Now we evaluate this from 0 to 10. Plugging in the bounds, we get the expression shown. Remember that e to the 0 is 1. This simplifies to negative 60e to the negative 1 plus 25e to the negative 2 plus 25. Using a calculator to find the approximate value, we get approximately 3.28 liters. So after 10 minutes, there are about 3.28 liters of water in the kayak. That concludes our session on advanced applications of definite integrals. We've covered area between curves, solids of revolution, and rates of change. Mastering these concepts is crucial for success in IB Mathematics, AHL. Remember to practice regularly, pay attention to the details of each method, and always visualize the problem. Thank you for watching.